Hey everybody, welcome back to physics. I hope everyone's doing well. Today we're going to be going through the series worksheet number 2 that I posted. I want to go through it nice and slow. I just want to make sure they're all feeling okay with this type of material. First thing I want to say is if you're feeling uncomfortable with this material, it's okay. I want to let you know that in the best of circumstances, for an in-class environment, students still tend to struggle with this topic. So if you're feeling confused, if you're feeling frustrated, it's totally okay. We're going to work through this together. We're going to keep doing this feedback back and forth. I want to try to make sure you guys are feeling okay with this stuff. But no worries, we're going to get through this together. Second thing is, I know I keep saying it over and over again, but I'm going to keep saying it because it's true. I miss you guys. I really can't wait to see you all again. I really hope I get to see you guys in class again. We're gonna get through this together. I know times are tough right now. Another thing, I just want to let you know that I've been kind of finding like a weird zen in doing these physics problems. I know you probably don't feel the same because it's tough learning this stuff and doing the problems, but for me, I'm finding kind of like a comfort in doing the physics. It seems to be the only thing making sense for me right now. Like when I was setting up the lights before, I was taking a look and I saw that they take 24 volts, 2 amps, so I quickly realized how much power my lighting is putting out over here. It's kind of nice, like getting a new understanding of the world around us. So take a second, go around your house, take a look at some of your electrical equipment. Every power cord or most power cords have the specifications right on it. You now have the understanding of what those specifications mean. So with that, let's dive in, get started, and stay safe, stay strong. We're gonna get through this together. All right, series worksheet number 2. We have a 60 ohm resistor, a 120 ohm resistor, and it's placed in series and attached to a 15 volt battery. An ammeter is placed into the circuit to measure the current through the 120 ohm resistor, and a voltmeter is placed to measure the potential difference across the 60 ohm resistor. That's a lot of information, so take it one little chunk at a time. The first thing you want to do is draw out this circuit. And even if they didn't tell you to draw the circuit, I would highly recommend to draw out the circuit. It's very nice to have the schematic right in front of you, so that way you don't have to keep referring back to this big chunk of text. You can take a look at your circuit, take a look at your verb table, and then things start getting a little bit more organized for you. So the first thing we're going to want to do is we're going to want to draw out this circuit, this series circuit based on the specifications that are given. So here's how I drew out my circuit. Like I mentioned before, I always like starting with the battery. Doesn't matter where you put the battery, as long as you're following the connections, everything should work out okay. So here's the battery. It's a 15 volt battery. We have our conducting wires, and we're connected to one resistor here. Swiggle line means resistor. We have another resistor here. And then I put my ammeter over here. And look at that. We have a series connection. A series connection is characterized by the current having to go through each component before it heads back to our source. Something I mentioned before, it doesn't matter what order we put these components in. As long as they're in series, it's going to have the same electrical properties no matter where I put these things. I could have put the battery here, 2 resistors here, and the ammeter here. I could put the battery here, all the resistors in the ammeter up here, and still connect it in series. It's still all okay. There's no one right way to do it, but you do have to make sure you follow the steps and following the rules of connecting these components. It doesn't matter which order they're in as long as they're connected in the right way. All right, so let's label what we have. We have our 15 volt source. We have our 60 ohm resistor, and it's telling us that the 60 ohm resistor has to be connected to a voltmeter. So that voltmeter needs to be connected in parallel. The voltmeter measures the potential difference from this point to this point. So that's why it has to touch those 2 locations and be connected in parallel to that resistor. Okay, so we have that. That means this has to be our 120 ohm resistor. Ammeter's good. I'm happy with the circuit. You happy with it? I'm happy with it. All right. Next thing, before I even read what the questions want me to do, I start drawing my verb table. I find a spot on my worksheet and I draw it out. I promise these verb tables are going to help you out. I always think back to when I was in school and the teachers would tell me, just draw the table. And I would think to myself, I don't need to draw no table. I can do this myself. But I promise you, trust me, this table is going to really guide you through these problems. So if you trust me, draw out the table and you'll start seeing these relationships pop up here and there. Our first goal is to find the reading in the ammeter. But before I even dive in and try to do that, I'm going to fill in the table with the information that I know. We know that 15 volts is being supplied to the circuit. So that is our total voltage, right? The source provides the voltage for the entire circuit. The V's here are the voltage drops across those resistors in particular. But the total section is for the whole circuit, so the source is the total voltage for the whole circuit. I also know that one of the resistors is 60 ohms. Does it really matter if I call it resistor 1 or resistor 2? Not really. As long as you're consistent through the problem, you'll still get the right answers. But me personally, what I like to do is I go around the circuit and I just pick resistor 1 and 2 and 3 as I'm heading back to the battery. That helps keep me organized. I am not an organized person. If you've seen my desk, you know that to be a fact. So I really need to make sure I follow these steps myself to keep myself as organized as possible. So one of the resistors is 60 ohms. The next resistor is 120 ohms. Plug that in. Okay. So the first thing we want to do is we want to figure out the reading in the ammeter. Now, what does the reading in the ammeter tell us? Well, it tells us the current going through the circuit. And because we know our series circuit rules, we know no matter where I pick, whether it's here, anywhere in the circuit, whatever current reading I get is the current in the entire circuit. So if I know any of these currents, I know the current everywhere in each component. So we need to find some way to find the current in this circuit. Well, I look and I see, okay, which of these can I get to based on the information that I know? I can't get to it in one step because I don't have enough information. I'm looking here at this cell. But another series circuit rule that I do know is the equivalent resistance. So R1 plus R2 in this case. So why'd I go there? Well, I'm looking at any of these cells. I can't figure out the voltage right away across any of these components, but there is something I can figure out. A lot of times, even if it's not directly the answer you're looking for, if you can figure something out, take that step and do it. You might not know exactly how you're going to get to the answer, but by figuring out the things that you can know, some of the things might be clicking as you go through the problem. In physics, it's much more about the process than it is about the product. Well, I can figure out the equivalent resistance because I know resistor 1 and I know resistor 2. We can just add them up. You have 60 ohms plus 120 ohms. And that's going to be REQ. 60 plus 120. Should be able to do that in your head, but if you have a calculator, it's okay. 12 plus 6 is 18, so this is 180. So the equivalent resistance of the entire circuit is 180 ohms. Okay, so that's the total resistance. By looking at this circuit and looking at this grouping of resistors, by adding more and more resistors in series, I'm increasing the total resistance of the circuit, the total the total amount that it's impeding the flow of the current. The more resistors I add, the total current of the entire circuit goes down. I'm gonna erase this. Okay, and with that, now that I filled in this cell, I see that I can figure out the current in the circuit using Ohm's law. Going across my total row, I know that R EQ, because that's the total resistance, is the total voltage over the total current. I didn't have to label the current total because the current everywhere for I1, for resistor 1, resistor 2, everywhere it's going to be the same, but it's kind of nice to see the labels of this row. Okay, plugging in what we know. The total resistance of this circuit is 180 ohms. That's how much it's resisting the current flow. Total voltage we know is 15 volts due to the source. I can find the current I. My total is fine. All right, doing some quick algebra, switching these two. 15 divided by 180 is equal to, look at my notes, do it on your calculator, that's what I did, 0.083333, and the unit is amp. I cut it off at one of those threes, just rounding, that's totally fine. The total current in this circuit is 83 milliamps, 0.083 amps. I can put that here. And that is my reading in the ammeter, because that's the current going through each one of these resistors. For a series circuit, if it asks you for the reading in the ammeter, it's asking for any of the currents through any of the resistors, because all the currents are the same. 83 milliamps. That solves part B for question 1. Okay, next thing we want to know is the reading on the voltmeter. That's here. And this voltmeter is measuring the voltage, the potential difference across the 60 ohm resistor. I'm going to erase. A lot of times with these problems, the first step is the hardest. Just getting started, getting your table, figuring out what you can know. But once you start filling things in, all the pieces start falling into place. I want to find the voltage across the 60 ohm resistor, that's V1. Using Ohm's law, R1 is equal to V1 over I1. Where did I get these subscripts? I just looked across my column. I'm looking at R1, so I'm looking over here. Subscripts are not necessary. I like them because it helps me to keep track of what I'm looking at. All right. So R1 is 60 ohms. V1 is what I would like. I want to know. Gotta blow before you erase or else it smudges. All right. That is 0.083 amps. Okay. Plug that into your calculator. 60 times 0.083 amps. You get a voltage of almost 5 volts. I got 4.98. If you rounded that to 5, I would totally understand. I'm going to keep it 4.98 though. That goes here. Remember, this table is for you. We have the work here, that answers the part, but by filling in the table, it'll help you with the future parts. I'm telling you, use these verb tables, they're super helpful. Okay, I'm gonna erase. The next part is I wanna find the power generated in the 60 ohm resistor. I hope this is clear for you guys that you can see, but just take a look at the worksheet and follow along that way. Gonna erase. Isn't this nice? Doing some physics. Physics zen in these crazy times. All right, I want to find the power generated in the 60 ohm resistor. Power, I'm looking in the P column. And in the 60 ohm resistor, that's here, that's resistor 1, I want that spot there. If you have any two of these, you have the information to find the power, because page 4 of the reference table, we have, 3 different ways to calculate the power. V times I squared R, or V squared over R. We could use any of those to get to the power. I like to go the simplest route. I'm just going to multiply these two together. P1 is the power on resistor 1 is equal to V1 times I1. Okay, the voltage is 4.98 volts. I1 is 83 milliamps, that's 0.083 amps. I'm gonna move my Disney glass. The answer, plugging it into your calculator, I got 0.413, I had another 3 in there, why not? Watts. The unit for power is watts. What this is telling us, because you always want to think, what does this number mean? That means that this particular resistor is dissipating about half a joule of energy every second. That's what a watt tells you, is how much energy is being dissipated every second. It's about half. Plug that over here. Okay, and that finishes off problem number 1. Yes, I still have cells empty, but guess what? Right now, I don't really care what these are. If you're feeling ambitious, fill them out. Why not? But for this particular problem, I am done. That's it. I've gotten everything I wanted to get. Okay. Another thing to keep in mind is that the thought process for parallel circuits is the same, but the rules are different. I'm still looking at my VERP table, but I need to keep in mind that I'm following different rules for filling out the table. But the problem-solving strategy is still the same. Here we're focused on series circuits, but we'll be looking at parallel circuits. Well, we have been looking at parallel circuits, but we're going to keep looking at all these different types of circuits. Okay. So, I'm going to erase, I'm going to get all set up, and we will start question number 2 on this worksheet. All right, let's take a look at question number 2. Reset up the whiteboard. I have question number 2 up on the screen. I am on the next page of my notes. All right. Here's the situation. We have a 220 volt DC source. A 220 DC voltage source is connected to 3 resistors as shown on the left. The current through the 50 ohm resistor is 0.50 amps. Determine the reading in the ammeter. I am not going to redraw the circuit, mainly so I have more whiteboard room, but feel free if you want to redraw it, but we have it right there in front of us. We don't really have to draw the circuit schematic. So, based on this information, we want to figure out all of these different parts of the question. Part 1 says, determine the reading in the ammeter. If you're comfortable with your series circuit rules, you might already know the current in the ammeter. But, still do this for me. Set up the VERP table because it's going to help you out with the other parts of this problem. I've been doing physics for a long, long time. I still set up VERP tables when I'm analyzing these circuits. Okay, so here, first thing we want to do is take a look and see what we know about this circuit. Well, it's given to me that R1 is 50 ohms. Let's plug that in. 50 ohms. It's also given to me that R2 is 75 ohms. Boom. And it's given to me that the total voltage is 220 volts. All right. Our first goal is to determine the reading in the ammeter, but take a close look at this question. It tells us that the current through the 50 ohm resistor is 0.5 amps. So, just going purely on what they tell us, the current here is 0.50 amps. But look at your series circuit rules. So you have our table in front of us, you have your page 4 of the reference table, we look and we see that the current in a series circuit is the same everywhere. Doesn't matter where I pick here, here, or the ammeter, the current has to be the same in every single spot. of the circuit. So the first question requires no work. What I wrote, if you really want to know, I just wrote 0.50 amps, and I wrote that I is equal to I1 is equal to I2 is equal to I3. Just so I have something down. But for this type of problem, for the Regents, it would just be report the answer. The answer is half of an amp. So we got this column of our vert table done. Going to erase. Part B, we want to determine the reading on the voltmeter. Now we look at the circuit and we see that the voltmeter is connected across the 75 ohm resistor. So the reading on that voltmeter is going to be giving me that cell of the vert table. Okay, so I want this. I want the voltage across the 75 ohm resistor. I look across, I see that we have two of these quantities. We can figure this out. We're going to use Ohm's law here. So for part B, R is equal to V over I. You want to be nice and organized, you can identify everything in that row. The value of R2 is 75 ohms. We want the voltage across that resistor, and the current is half an amp. Okay. So, doing some algebra, 75 multiplied by a half is equal to 37.5 volts. You can use your calculator, that's totally fine, but exercise your math muscles. Half of 75 is going to be 37.5 volts. Box that, throw it in our table. Circuits are very puzzly. Once we get more and more pieces, the puzzle starts getting easier to solve. All right, that's part B. Part C, I want to know the equivalent resistance of the circuit. I'm going to erase. Now, I know what you're thinking because I think the same thing. Okay, the equivalent resistance is just R1 plus R2 plus R3 in a series circuit. But then we look, oh no, I don't know R3. How can we find the equivalent resistance if we don't know R3? A few ways to handle this. You are 100% allowed to go to the next part of the problem if you don't know this one yet. I can't figure out the equivalent resistance. Let's try the next one and see if we can go back and figure it out. But if you don't want to do that, we actually do have enough information to find the equivalent resistance. Maybe by not adding up the resistors, but look at your total row. I know the total voltage and the total current through this circuit. By having these two cells, I can figure out this cell, the total resistance of the circuit. Let's do that. Req is the total resistance. That's going to be equal to V total over I total. Okay. So let's plug in what we know. Req is equal to V total is 220 volts over half an amp. 220 divided by a half is the same thing as multiplying 220 by 2. Req is equal to 440 ohms. Box that, put it in. Okay. So, that's it. We have the equivalent resistance of this circuit. Let's erase. There are more than one way. There is more than one way to get to the answer in a lot of cases. There we used Ohm's law to figure out the equivalent resistance. That's 100% valid. For every row, everywhere in the circuit, the electrical rules still apply. I could look across, I could use Ohm's law across the total row. That is 100% valid. All right, now that we know the equivalent resistance, let's take a look and see if we can find the value of resistor 3. That's here. This is C, this is D. I want to find the value of resistor 3. Okay, Now we could use our equivalent resistance equation. Req is equal to R1 plus R2 plus R3. There was another resistor plus R4, but we only have 3 here. The equivalent resistance we just found to be 440 ohms is equal to R1 is 50 ohms. R2 is 75 ohms. Run out of space here. There we go. Plus R3. Our goal is to find R3. I know everything else but R3. We can totally solve this equation. 440 minus 50 minus 75 will give us R3. R3, I worked it out to be 315 ohms. All right, let's plug it in. Perfect. That is the value of resistor 3. Next, we're almost done. Appreciate you sticking with me. We want to find the power generated in R1. That's part E. Power generated in R1. That's our P column. And we're looking at R1. Okay, how can we figure out the power? We have a lot of options when it comes to figuring out power. We can't do V times I, but we can do I squared times R. I guess I'll erase this. You see it? Write it down. Okay, so now we're doing part, what is this, E? Power in resistor 1 is equal to I squared, that's I1, squared times R1. Okay, we know this. Power is equal to, well, there's a half an amp everywhere in this series circuit. R1 is equal to 50 ohms. 0.5 squared is 0.25 multiplied by 50. That's a quarter of 50. So we get 12.5. What's our unit for power? It is watts. This resistor is dissipating 12.5 joules of energy every second. That's what the power means. 12.5 watts for resistor 1. Okay, and next, finally, part F. I'm going to erase. Part F asks us, which resistor generates the most energy in the circuit? Give a reason. Okay. Reading this question at first, you might be thinking, I have not been thinking about energy at all here. I've been thinking about voltage, current, resistance, and power. But if you know what these quantities mean, you already know how to get to the answer here. Which one generates the most energy? Well, power has to do with energy. Power directly tells you how much energy that resistor generates every second. Which resistor is going to generate the most power? Okay, how can we figure that out? Well, I see that we know all 3. We know the current for these 3 resistors, and we know the values of those 3 resistors. We know power is equal to I squared times R. Well, all the currents are the same, so whichever resistor has the greatest resistance is going to generate the most power. We can look and we quickly see that has to be R3. To figure out the power generated, you'll take 315 multiplied by 0.5 squared. That'll tell you the power. But R3 has to be generating the most energy in this circuit. The most joules per second will be generated by resistor 3. That was a little bit of a tricky one, but I hope you got it and I hope you followed along with me. Again, this is about the process, not the product. I know for a lot of through schooling, if you feel like if you don't get it at the first try, that you kind of get penalized for that, but that's not what physics is all about. Physics is about looking, trying, potentially not doing well the first time, but going back and figuring out where we went wrong. So we went back to this worksheet, we worked it all out together, and hopefully you feel a little bit better about series circuits and circuit analysis here. I'll be doing a very similar video analyzing parallel circuits. The thought process is the same, but the rules we follow are different. So we'll get to that very, very soon. Be very careful, keep track of things in your table, and make sure you know which rules we're looking at. Again, I really hope everyone's doing well. I miss you guys, and hopefully I'll see you soon, and you'll definitely see me in the next video.